Okay, so today's notes are on linear programming, and our content objective is going to be to solve problems using linear programming. Sorry. Our language objective is going to be to use correct terminology when explaining linear programming, including constraint, feasible region, and objective function. So I've already written definitions for two terms here, including linear programming. So linear programming is a method for finding a maximum or minimum value of some quantity given a set of constraints. And constraints are just limits or boundaries that are put on a certain region or feasible region, or to create a certain feasible region, which is our next word. So given these constraints, a feasible region will be created, which contains all the points that satisfy all the constraints. So this is going to be relevant when we're talking about certain word problems. So like you can't have negative values, but it has to be greater than this and less than this linear function. So it'll all fall within this certain feasible region. We probably won't get to a word problem in the notes today, but that will be our focus in class for that. But I want to make sure that we have the basics and the concepts down, or the skills we need to solve problems like that. So this might sound like a lot given that we don't know what this actually is looking like. So I'm going to draw a little demo graph here. So if we have just our normal XY axis, you could have a use linear programming to create a feasible region that could look something like this. So I'm going to use dotted or dashed lines to demonstrate my point. So you could have a line going here and here, and another one going this way, and this way. So all of these dashed lines, in this case, though they do not necessarily need to be dashed lines, just in this example they are, these would be our constraints. The feasible region would be the shaded area. So if it was less than that and greater than this and less than that and greater than that, it would all go like this. So the shaded area, which this is in this situation, is going to be the feasible region. So our feasible region is the area that gets enclosed by all of those constraints. So the way we're going to use this feasible region or linear programming to find the maximum or minimum is with our objective function. So we're going to use an objective function because this is going to be the model or line of the quantity you are trying to maximize or minimize. In our example problem we're going to do together, it's just going to be a general linear equation, but often in real life contexts, it will be your cost that you want to minimize or your profit that you're trying to maximize. So you're trying to minimize cost, maximize profit. You can use an objective function to decide, or objective function representing one of those two things to decide or to solve your linear program for. So I'm going to flip the page. Before we jump into our example, I want to emphasize one last key point here. So I'm going to write key point. If there is a maximum or minimum of an objective function, so the definition we just went over, granted that it is linear. So this is objective functions that are linear specifically. It occurs at one or more of the vertices. of the feasible region. So this is tying in with what we've been doing because our feasible regions tie into our linear inequalities that we've just done, because that's how we determine our shading. And then our vertices are going to be created by the intersections of lines, which is where our systems intersect, or where we'd solve for their intersection point or the solution of systems. So we're going to use the vertices to determine the maximum or minimum. So we're tying in both our linear inequalities and our solving systems to create these linear programs for maximums or minimums that we want to find. So the example we're actually going to jump in with, I want us to find or determine what point in the feasible region maximizes P for the objective function P equals 2x plus y given the constraints. And I will write them all right here. So I'm going to squeeze them all in right there. I have x plus 2y is less than or equal to 5. I have x minus y is less than or equal to 2. X is greater than or equal to 0, and y is greater than or equal to 0. So these are my 4 constraints. And to solve this, I'm going to do my 2-column notes. I might have to turn onto a separate page just as a warning. But the first thing I'm going to do is graph my constraints. And to do that, I need to rewrite some of my linear equations. Into slope-intercept form. So I'm going to first do that with my first 2 equations. I have x plus 2y is less than or equal to 5. So I subtract x from both sides and I get 2y is less than or equal to negative x plus 5. I divide by 2 and I get y is less than or equal to negative 1/2 x plus 5. So my other equation, I have x minus y is less than or equal to 2. I add or subtract x from both sides and I get negative y is less than or equal to negative x plus 2. I multiply by negative 1 and I get y is greater than, since I need to flip the direction of my inequality, greater than or equal to positive x minus 2. So those are my 2 linear equations in slope-intercept form. The other 2 constraints are just a vertical line and horizontal line, so I don't need to rearrange those. So the next thing I'm going to do is actually graph them. So I know since x is greater than 0 and y is greater than 0 are 2 of my constraints, I only need to worry about the, let me make this a little longer. I only need to worry about the positive quadrant. So since I want to graph negative 2, I'm going to go a little bit lower. So I'll put my negative 2 down there, and 1, 2, 3, 4, 5. So I'm going by ones. Okay, so now I have my XY grid. I'm just going to go ahead and graph my different lines. So I start with the first one at 5, and I'm going down. Oh, sorry, I didn't divide that by 2. That's 2.5. Apologies. So that's 2.5. I forgot to divide my 5 by 2. Important to do. So I'm actually starting at 2.5 over here. So 2.5, the coordinate 0, 2.5. And I'm going down 1 over 2. So down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. And I'm going to graph, oh, my paper moved. I'm going to graph that line. It's a solid line because it has the equals to sign. So there's my line there. Then I have y, positive x starting at negative 2. So I go up 1 over 1, up 1 over 1, up 1. And it's going to continue up like that. And then last but not least, the x is 0 and y is 0 is just my x and y axes. So this one, since it's less than that, I'm shading downwards. This one's greater, so I'm shading upwards, and same with these. It's greater than x is 0, so it's going that way, greater than y is 0, so it's going that way. So I'm shading in this bounded region as my solution set. So that is the feasible region of my linear program here. So I've found my feasible region. I've shaded it, which was step 2. Shade the feasible region. And now that I've done that, I know based on the key point we previously mentioned that my maximum for P is going to be at one of these vertices. So where one of these intersects. And so they're going to be at 0, 0, 0, 2.5. This one is at 2, 0, because it's my x-intercept. And this one I can see they intersect at 3, 1. So that's, I graphed precisely enough to be able to figure that out. So step 3 is determine the coordinates of your vertices, which is what we were just doing. And I want to make a note, in this case, I was able to solve for them all by graphing, but in some situations, you might have to solve a system algebraically when necessary. I'll start that in this line. So solve the system algebraically when you need to. In this case, you didn't have to because we could see it on the, we could solve it graphically, but if necessary, make sure you solve for it algebraically. So the last step, or second to last step, we're going to substitute vertices into our objective function. So I'm going to take each coordinate point. So I start with 0, 2.5, and then I have 0, 0, and then I have 2, 0, and 3, 1. So I just all the vertices, and I'm plugging them into my objective function, p equals 2x plus y. So when I plug that in, I get p equals 2 times 0 plus 2.5. Should write this a little neater. 2 times 0 is 0 plus 2.5 is 2.5. Here I plug in 0, 0, and I get p is equal to 2 times 0 plus 0, which is just 0. If I plug in 2, 0, I get p is equal to 2 times 2 plus 0, which is equal to 4. And last but not least, I plug in 2 times 3 plus 1, which is equal to 6 plus 1, which is 7. So now, since I was trying to figure out the maximum, so I was maximizing P, which could represent something like profit, I want to choose the profit that is, or the P value that is maximized, which is 7. So since 7 is the maximum value that results from one of my vertices, that will be my maximum coordinate. So my solution, last step, we were at our solution, and it's going to be that the P is maximized at the point 3, 1, and that is our answer. You can say with a value of 7 if it's relevant in the context of the problem, but that is our solution nonetheless. It's at the vertex 3, 1 with a value of 7. Make sure you write down any questions, comments, concerns you have on this so we can go over it together in class.